In today's video, we are going to make an AI system called flocking. It's a system used mainly to simulate crowd movement behaviors. In this project, we will try to simulate different group of fish that will be steered by various parameters. Every AI agent movement is based on three main behaviors. Cohesion, the average world position of other agents in a given radius. Avoidance, the average vector of directions to neighbors in a given radius. And alignment, this will be also a vector which is an average of the forward directions of agents in a given radius. Using these three behaviors, we can achieve what we can see right now on the screen. Let's begin. For this project, we will be using Unity 2019.2 and a lightweight render pipeline template. First, I downloaded a fish model and created a simple shader in a shader graph. You can use the starter package in the description below, it contains all used assets. First, create an empty game object called flock and add a script also called flock. Open it in your code editor. Let's start with writing the functionality for instantiating our units. So for that, we will need a visible in the inspector field for our unit prefab, an integer for the number of units, and a vector3 to define the spawn bounds. Let's also keep all instantiated units in an array, and let's make that a property. In the start method, add a new method that will handle the spawning of units. In this method, first we will initialize our all units array with length of flock size, which will be a variable assigned in the inspector. Then we will iterate through all of the units. For every unit we will pick a random position in bounds, so let's just get a random vector3 using the random.insideUnitSphere property and multiply it by our bounds vector. Now we can add that random vector to the flock position. Instantiate a new unit and assign it to the all units array. As a position, use our random position. Let's also set a rotation. It will be a rotation with a random y-axis angle. So use the quaternion.euler method that will convert a vector3 to a quaternion. Now back in Unity, create a new folder called prefabs and drag and drop our fish from the scene and then remove it. Next, add a flock component to the flock object and fill the inspector fields. Add a unit prefab, use the prefab that we have just created. I will set the flock size to 100 and spawn bounds to 10 in X, 5 in Y and 10 in Z axis. Hit play. And as we can see, the fish are being spawned correctly. Next, create a new script called flockUnit. This script will implement all the flocking behaviors. Let's declare a method that will move the unit. First, we will calculate the cohesion vector, so create a method that will return a vector3 called calculateCohesionVector. Declare a vector3 that this method will return and initialize it with a 0 vector. To calculate the cohesion, which as we said before is an average position of all units in a certain radius, we need a collection of all neighboring units. Let's declare a list that will store those units called cohesion neighbors. Also, the units should not detect other units that are behind them, so let's add a variable for the field of view. Before any calculations, we need to find the neighboring units. Let's create a method for that, and we will invoke it first in the moveUnit method. First, clear the list of cohesion neighbors. We will have to iterate through all of the units that are part of the same flock, so we need a reference to the flock component that spawned this unit, and a method called assignFlock that passes the flock object in the parameter and assigns it to our flock field. Back in the flock script, after unit spawning, call the assignFlock method. Also change the prefab as well as all units types from GameObject to flockUnit and pass the flock itself as a parameter. Now back in the findNeighbors method, get all units from the assigned flock and iterate through all of them. Let's store the current unit in a variable. Now let's check if we are not iterating through ourselves, and if not, then we will calculate a distance between ourselves and the current unit. We will use square distance because it is a much faster method. Calculating a distance requires a square root calculation, which is a pretty expensive method, so we want to avoid it, especially if you want to do it every frame. Let's also cache the transform components as a property because we will call it a lot and the stored transform is a little bit faster to use. Now we have to check if the calculated distance is shorter than some kind of detection radius. Let's create that radius in flock script because it will be shared by all flock units. Add a header to the spawn variables and add another header for detection distances. The first distance is a cohesion distance. Add it as a serializable field. Also add a property to return this distance. Now we can compare the calculated distance to the cohesion distance. Remember that it has to be to the power of 2 because we are comparing it to distance squared. If the distance is shorter, then add the current unit to the cohesion neighbors. Back in the calculate cohesion vector method, declare the return vector as a vector 3.0. Declare an integer that will be a number of units in the cohesion distance that are also in the field of view. If there are no units in the cohesion radius, just return vector 3.0. Next, we have to iterate through all of the cohesion neighbors and check if they are in the field of view. Let's add a new method for doing this that will take a neighbor position as the parameter. This method will return true if an angle between our forward direction and the direction to the neighbor position is less than the field of view set in the inspector. If the neighbor is in the field of view, increment the field of view neighbor's number and add the neighbor's position to cohesion vector. If we didn't find any neighbors in the field of view, that would mean that the cohesion vector is still 0 and we can just return it. Now divide the cohesion vector by the number of neighbors in the field of view. We have to subtract our position because the cohesion vector right now is an average world space position and we want to convert it to the local position of the unit. And lastly, let's normalize it and return it. Back in the flock script, add a range to cohesion distance field for easier manipulation. Now let's use the calculated cohesion vector to drive the unit. We will use the vector3.smoothDump method to get the vector for that frame. Add a vector3 field for a current velocity for the smoothDump method to pass as a ref parameter. Add a serializable float called smoothDump. The lower this value is, the closer to the cohesion vector we can get in a frame. Therefore, it will rotate faster. Normalize the calculated vector and multiply it by the speed value that we have to assign first. Add a private field called speed. Assign the move vector to the forward direction and increment the unit's position by the move vector times time.delta_time. In the update method, we will iterate through all of the units and call the moveUnit method on them. In the flock unit script, let's add a method that will initialize the unit's speed by simply passing it in the parameter. In the flock script, add a new header for speed variables. We will have a minimum and a maximum speed that each unit can reach. After assigning a flock to a unit, let's also initialize it with a speed which will be a random value between the minimum speed and the maximum speed. Let's also add ranges for the minimum and the maximum speed. In Unity, find the fish prefab and add a flock unit component to it. Set its field of view to 270 and smooth dump to 1. Find the flock in the scene and assign the fish prefab to the flock unit prefab variable. Set the minimum and the maximum speed to 1 and the cohesion distance to, let's say, 5. Now press play. As we can see, the fish are grouping together and in the end they will get to one group in kind of a ball shape. If we increase the cohesion distance, the fish will go apart, and if we increase it again, they will regroup. So a pretty nice behavior already. Let's calculate speed based on the neighbor's speed. So add a method called calculateSpeed. We will set the speed value as an average speed of all neighboring units. So let's iterate through all of them, but first reset the speed value and add a neighbor speed to our speed. After the loop ends, divide the calculated speed by the neighbor's count and clamp it between the minimum and the maximum speed. Let's make properties for the minimum and the maximum speed to get those values. Back in Unity, set the minimum and the maximum speed to, for example, 2 and 4 and hit play. Now the fish are moving a little bit more randomized and adjust their speed based on their neighbors. Also, as we can notice, some fish are stopping and there is an error in the console. So let's fix that. In the calculateSpeed method, to avoid dividing by 0, let's return the minimum speed when there are no neighbors. Now hit play again. Now we have the proper behavior. This is just the beginning and the results are already pretty good. Let's go further and implement the rest of the behaviors. Avoidance and alignment behaviors will need similar variables as cohesion, so let's just copy and paste the distance fields 2 times and change their names. In the moveUnit method in the flockUnit script, copy the line that calculates the cohesion vector. Copy it 2 times and modify the variable names. Next, declare a moveVector as a sum of all of those vectors. Let's add some spaces and change method names. Now generate those methods and let's start implementing them. Both of those methods will look similar to the calculateCohesionVector method. First we declare a vector to return, but in case of alignment, when there are no neighbors, we want to return the unit's forward vector. Next, declare an integer for the neighbors in the field of view. But beforehand, we will check if our alignment neighbor list is empty. We need to add that list in our class. Let's add lists for alignment and avoidance together. Let's also find those neighbors based on their distances, just like we did for cohesion. Now we can use the alignment neighbors list in the calculateAlignmentVector method. We iterate again, but this time through alignment neighbors and check if they are in the field of view. If true, then increment the neighbors in the field of view number and add the position of that neighbor to the alignment vector. Now, if there are no neighbors in the field of view, return the unit's forward vector. Otherwise, divide it by the neighbors in a field of view number, normalize the vector and return it from the method. Let's copy the method that we have just written, so we don't have to type it all again. Change the alignment vector to the avoidance vector and initialize it with vector 3.0. Change all variable names from alignment to avoidance, and instead of adding the position of a neighbor, we will add a vector that is opposite to the direction to that neighbor. We also don't need the field of view number check, cause it will not change anything. We forgot to clear the neighbors list, so let's just do that. Last thing to finish our basic behaviors is adding weights to every behavior type. This way we can build different flock behaviors that will favor different behavior. Let's add them similar to the distances in the flock script. In the moveUnit method, we will multiply each vector by its weight. Remember that all behavior calculating methods return normalized vectors. In the smoothDump method, change the cohesion vector to our move vector as a parameter. Go back to Unity and hit play. Now, with the alignment behavior present, the fish will not swim in a ball-like shape anymore. They will group together and swim ahead. If we bump the alignment weight value, they will go pretty much straight forward. When we decrease the alignment weight, the fish will kind of stop and swim around themselves. Let's click play again, get rid of the alignment behavior so they don't swim away, and check the avoidance behavior. If we increase that behavior's weight, we can see that the fish disperse a little, because they will try to avoid any other units within the radius of length 1. So they still group together by the cohesion force, but when they are close together, they will try to avoid each other. It also helps with meshes not overlapping each other. Now play around with those values and see what flock behaviors you can get. Change weights and distances and think of some logical behaviors. As we saw earlier, the fish tend to swim away and kind of lose their flock. Let's combat that by adding bounds in which the fish can move. Go to the moveUnit method and add another vector 3. Let's call it bounce vector and declare a new method to calculate it. First, we will calculate a direction from our position to the center of the flock. Now, let's create a boolean variable that will be true if we are close to the flock bounce. But first, we need to know what the bounce radius is. So let's add a bounce distance and weight. Back in our method, if the distance to the center is, let's say, in 90% of the bounce distance, then we are close to the bounce. If that's true, we will return a direction from ourselves to the center of the flock. Otherwise, we return vector3.0. This method, of course, returns a vector3. Now, back in the moveUnit method, add the bounce vector to the move vector, so it takes the bounce vector into account in the unit's movement calculation. Go back to Unity. Let's also bump the bounce distance in the flock component. Set the bounce distance value, let's say to 20. Maybe change other behaviors, because why not? And let's set the bounce weight to the maximum value, so that we are sure that the fish will come back. Now hit play. I set the behaviors that they kind of cancel each other, but this way we can see them bouncing back when they are close to the bounce. As you can see, they go back pretty sharp because we set the bounce behavior weight to the maximum value. Let's change some values so that our flock behaves a little bit better. We still can see that the fish will not leave their bounce. Now let's prepare the scene to look a little bit like a bottom of the sea. First, create a terrain with some hills and valleys. Let's say that's what the bottom of the sea looks like. Set the camera and the flock positions and press play. And here we go, the flock on the bottom of the sea. Let's disperse the fish a little bit with the avoidance weight. And move the flock position so the bounce position will move too. That will force the fish to follow the flock transform. We have one problem. The fish don't detect the terrain and can swim through it. If we go below the terrain, we can see some fish got there. We would like to avoid this situation. We have to use some custom solution for that. Let's go back to the flock unit script and implement obstacle avoidance. So add another vector in the moveUnit method and call it obstacle avoidance vector. Same as with everything else, we will need a method to calculate a vector, a weight and a distance. So let's add a calculate obstacle vector method, a weight and a distance. First, in the method, return a vector free that this method will return. We are going to use raycasting to detect the obstacles, in our case, the terrain. Let's raycast from our position. The direction of a raycast will be our forward direction. The distance will be the obstacle detection distance. Also, we would like to raycast only objects on a certain layer, so let's declare that layer in a field. Now we can add this layer as a parameter in the raycast method. If we do hit an obstacle in front of us, we would like to find a direction to turn to. So let's add a method that will return that direction. Let's also return that vector. Of course, the return type should be a vector3. In the find best direction to avoid obstacle method, we will raycast in 4 different directions. Then we will check which of them don't hit any obstacle in the detection range and pick that one. If all of the raycasts in those directions hit an obstacle, we will pick one that has the longest distance to the obstacle. So first, let's declare a variable for the maximum distance to an obstacle and the current direction. Now we should iterate through those 4 directions. To do so, let's declare an array of local directions that we will raycast to. Now let's raycast in all of those directions. Declare a raycast hit variable and calculate the word space direction from the local direction. For this, we will use the inverse transform direction to get the local direction from our world space forward vector. Add also the current direction vector. Let's change the variable name to current direction. Now let's raycast from our position to the direction that we just have calculated and see if it hits any object on the obstacle layer in the detection range. If it does, then let's check the distance from that point to our position. We forgot to add the out parameter in the raycast method, so let's fix that. Now we will check if the distance is longer than the current max distance, and if so, that means that this direction is better than the previous one, and we assign the current distance value to the max distance variable and the current direction vector to the selected direction variable. Let's change the direction variable name for clarity. And in the end, let's return the normalized selected direction vector. We introduced a bug in calculating the raycast's direction. The direction parameter in the raycast method has to be word space, and we calculated the direction in local space. To fix that, we have to use the transform direction method instead and pass the direction to avoid obstacle as the parameter. That way we transform the direction from the parameter in local space to the direction in word space. We still have an issue. Now every time the unit hits an obstacle, it will raycast in those 4 directions and pick one. That can lead to picking a different direction every frame, and in result our fish will shake like crazy. To fix that, we should store the selected direction and first check if this stored direction is still valid. We will store the direction only when the raycast in this direction didn't hit anything. That way we are sure that this is a safe direction. Let's declare a variable for this stored direction. We should reset this direction every time we don't have any obstacle in front of us. Let's add this to the obstacle avoidance vector method. Now in the findBestDirection method, first we check if our stored direction is not null. And if so, we will check if it still does not hit any obstacle in the detection distance. If it doesn't, this direction is still good and we return it. Now we should store this direction somewhere. As we said, we will store a direction in which we don't hit any obstacle. So back in the findBestDirection method, add an else statement to the raycast method. So in this case, we set the selected direction to current direction, set the stored direction to current direction, and just return it. We don't want to check any more directions, this one is good enough for us. Lastly, let's add our obstacle vector to the move vector in the moveUnit method. Back in Unity, let's add a new layer called obstacle. Select the fish prefab and set the obstacle layer in the inspector. This layer could be also defined in the flock script. Also set the local directions that we will use to raycast when looking for a direction to turn to. I will set them to left, right, up and down vectors. Probably I should set the z-axis to 1, but this should work also. Assign the obstacle layer to the terrain. Don't forget to set the obstacle weight and the distance. Hit play. We set our flock position in between those two hills to clearly see fish avoiding the terrain. As we can see, our fish move to avoid the terrain, but they don't just turn away from it, they try to slide near the surface, and that's exactly what we wanted. Let's increase the avoidance and see if they go through the terrain. As we can see, the fish dispersed, but they still try to avoid the terrain. Now, when we decrease the obstacle weight, we can see that the fish start to go through the terrain. Now, let's add a little more flocks to the scene. Hit play and take a look. Here we go, a bunch of fish swimming around. You can change parameters on every instance of a flock and have lots of different behaviors and make the scene look more realistic. Now I think we would like to swim around with our fish, so let's add a script that will control the camera. So create a new script called camera controller and add it to the camera game object. In the update method we will do three things. First we will get the player input, then based on this input we will change the camera's position and rotation. Before we implement anything, let's declare the necessary fields. We will need constant string for axis names, horizontal and vertical for the translation, and mouse X and mouse Y for the rotation. Now declare floats to store the input from those axes. So add a private float called horizontal input, a private float called vertical input, a private float called mouse input X, and private float called mouse input Y. In the getInputs method, we will just store those inputs in our variables from proper axes. In the handleTranslation method, we have to create a vector3 that will move our camera. Let's create this vector with the horizontal input as X, so the horizontal input will direct us in left or right direction, and the vertical input as Z, which will direct us in forward and backwards direction. Next, use the transform.translate method to translate us in this direction. Remember to multiply this by the time passed in this frame, and also some speed value that we will assign from inspector. We will leave the y-axis as 0 because the translate method by default moves us in a local space. That means that we will move based on our camera rotation, which will be handled in a second. In the handle rotation method, first we will store the delta rotation that should be applied in this frame. I've made a mistake and typed mouse input Y for Y rotation, but in fact we want to rotate in Y axis based on left and right mouse movement, which is the mouse X axis. We will fix that in a minute. Let's create a variable for rotation speed, just like for move speed, and multiply the input by the time passed in this frame and the rotation speed. We will need two more fields to store our current rotation in the X and Y axis. Back in handle rotation method, add the rotation applied in this frame to our current rotation in Y axis. Let's do the same for the rotation in the X axis. So first calculate the delta rotation for current frame and add it to the current X axis rotation. In case of X axis rotation, we would like to limit the rotation so we cannot flip around. Let's clamp the current rotation from, let's say, -90 to 90 degrees. Now, create a quaternion based on our axis rotation. Quaternion.euler will convert a vector-3 to a quaternion, so let's just use it. We don't want to turn in the z-axis, so let's leave that as 0. Lastly, in the start method, let's lock the cursor and initialize the current rotation y and z fields to our transform rotations in those axes. Back in Unity, set the rotation and move speed in the inspector to, let's say, 10, and hit play. Now we can swim around with our fish. Also, as we see, the frame rate is pretty low, but this is something that we will handle in the next video. Lastly, let's make our scene look a little bit more like the bottom of the sea. We will start with removing the skybox, so set the background type on the camera to a solid color. Now let's find some water texture to put on our terrain. We will use the free stylized water texture from the asset store. Let's import this. The imported material in the project view are displayed as a plain magenta color, which is an indicator of a shader problem. In our case, the material is not compatible with the lightweight render pipeline. To fix that, go to Edit, Render Pipeline, Lightweight Render Pipeline, and click Upgrade Project Materials, then click Proceed. Now our materials look fine. Let's use this texture and paint the whole terrain with it. Go to the light settings and add some fog. Use a color similar to our terrain. I will use the exponential mode with density of 0.08. Now hit play and let's take a look at the finished project. And that's it, guys. You can find the whole project on GitHub in the description below. I hope you enjoyed it and please like and subscribe if you like my content. There are new videos every Monday. Also leave a comment, I'm happy to answer all of your questions. Take care.